channel, so your blues. You have your GFP, which is 488-ish. You have your Cy5, which is your far red, so 647. And then you have PE, which is kind of an offshoot one. It's 488, but then your emission spectra is a little bit further. It does have a monochromator, so it can do your plate reading, so absorbance, fluorescence, luminescence. Any typical assays that you do, BCA, the Bradfords, luciferase assays, they often be done here as well. You do have injectors, and while it's not completely set up right now, you will be able to do live cell imaging over long periods of time with our CO2 controller right here. Objectives for the imaging portion. You have your low mag objectives. You have a 4x, you have a 20x, and a 60x high magnification objective. Your 20x and your 60x, because they're high magnification, they do have something called a correction collar. And we'll talk about this later, and maybe I'll even pull it out so that you guys can play with it. But because this is kind of like it's meant to be automated, we allow for anyone to use a variety of different plate types. So you can imagine that if you're using a glass slide, it's very thin compared to maybe a 6-well plate. It's a thicker bottom. In order to account for that, we have a correction collar, and we'll go over that later. Let's see here. I want to show you kind of all the accessories that it comes with. Well, not just accessories, but this is, while you're not going to be using it that often, this is the calibration plate. So you would typically never use this unless you need to move the instrument from one location to another location. If you replace anything on the inside, so right now you have 4 different colors, right? And the system can take 4 different colors. You have your blue, green, your off green red, and then your far red. If you decide to add more colors later on in the future, for example, Tritsy, which is like for Floydin, rhodamine, and you want to swap it out, you would need one of these. It's not required that you do like a preventative maintenance type thing every year with this. Only when you replace it or only when you move the instrument.
Is preventative maintenance included in our package? Oh no, I think we had some sort of a warranty.
There is warranty. I think there's like a 3-year or 5-year warranty or something like that.
Yeah, and then we might add more once we have need.
You can always get the preventive maintenance at any time as long as the warranty is up, which can sometimes be useful especially if you use the dispensers and you you spilled something, because it includes taking the whole thing apart and cleaning everything, including the optics, and that improves the lifespan of the instrument too. So that will be like my field. So if you're ever interested in that, I leave my part on the instrument as well. You can also reach out to me if you ever have questions about, like, say you got an error message or like anything is up that you're just not quite sure what it means. You can also reach out to me and we figure it out together.
Okay. So the maximum of the cubes that we can have is 4 at any given time.
4 at a time.
Okay, so we're at max.
Yeah, and that's it's supposed to be user-friendly, interchangeable. So essentially, hopefully in your group you'll have a power user. That's what we call it, power user. That is very familiar with the instrument, and they'll be able to swap things in and out.
It'll be Masood.
you're being volunteered to be the power user.
Memory of the lab.
Yes. But again, it's something that's very easy to do. And then before we leave at the end of the day, I'll show you how to go over that. This is an adapter for slides. So if you do want to do slides, they're right here. And I think that's it for the kind of the general hardware introduction. Any questions regarding hardware?
So you mentioned the injectors are up top. Is that separate from like the gas control? Oh,
Yes.
so there are 2.
Yes.
So where would it draw from if we were to inject?
So they would typically draw from here. This is kind of an example of how you would do this. People typically use like a falcon tube, just place it in here. I mean, if you're working with smaller volumes, like you're doing luciferase assays, you just somehow find a way to place, or even just remove these metal pieces and then just put a rack there. That would work as well.
And then, so, like with the injectors, I didn't really look closely into that, but does it inject into all the wells or like sequentially?
You could decide how you want to do it.
So you can do full plate, like injection into all the wells at once?
So by default, if you do not choose if you do not choose well mode, then it will inject into all the wells.
Okay.
Typically people don't do that. Typically people inject into one well and then do a reading.
Yeah.
Especially for like faster kinetics. So if that's the case, then we'll go over on how to set that up, which is usually the standard read.
And it would be sequentially.
It will be
Yeah, so
sequential.
it's not like a 96 well
Yeah.
manifold that will
yeah.
do it at the same time. It's 2 pins that you can use to inject one well after another.
Okay. Well,
Any other
we'll
questions?
ask you when it comes to that, when we have to do that.
Okay.
Okay.
Any other questions?
And we do have temperature control, right? On
Oh
this
yes, sir.
instrument.
Yeah, temperature control up to 45 here.
Okay. And is there a separate switch for it, or is it like programmed through your software?
So the temperature control is going to be programmed in the software. There's a button that you can turn on and off.
Okay.
And if you're running an experiment, you'll also include that in your protocol. For CO2, it's as simple as just hitting the switch button, and then you have your on and off.
Okay.
Okay. Now, are we going to be playing with samples today? Any samples today?
We decided to leave it till tomorrow since not all of us can make it. So we thought this would be like an overview, and then tomorrow we'll do the slides and the plate assays.
I do have a sample. It's a fixed set. It's not the best. This is about a month and a half old, but there's still cells on here. At least when I checked last week. We're going to be looking at fibroblast cells.
Okay.
And they're staying with a DAPI for the nuclei. It has a GFP tag, and then for hopefully we could hit it in the reds. Hopefully we can hit it. Yeah, maybe if we can't see it, we'll see the cytoskeleton. Let's see here. Oh,
Is that image also taken with citation 10?
this image is actually taken with citation 5.
Oh.
So I'm gonna just open this up real quick so you can see. So the citation 10 is supposed to be a 2-in-1 type of thing, or 3-in-1 type of thing, where you have your wide field instrument on the right hand side, you have your confocal on the left hand side, and then you have your monochromator for the plate reading.
Mhm.
In this case, on the right hand side, you do have the wide field right here. And this includes, well, on the right hand side you have your objectives, and then on the left hand side you have your wide field imaging cubes. Everything over here is the same as the citation 5. So these images came from this right side.
Oh, nice.
So yes, so if you get lucky, you can get nice images like that too.
Yeah. If we get lucky and get our answer, then we'll upgrade with the confocal, which we'll find out next month.
That would also be me.
That will also be with you.
Once that's happening, I'll come and do the upgrade.
Okay. So how does this wide field compare to other like similar microscopes in terms of resolution? Because on our CFI, like I have one and Xavier has one as well, we have each one like microscope, like we have budgeted for one microscope each, but now we're thinking if we have this, maybe we don't need those, and we can use it to upgrade this or for some other purposes.
Which instrument do you have right now?
Oh, mine is a very basic like Leica microscope for cell counting, but I think he has a fluorescence microscope on his, like a basic one.
Okay.
Yeah, so it might be worthwhile that we combine our budgets and get.
Well,
like,
we'll see how it looks like today.
Mhm.
I'm going to show you this 96-volt plate, and then I'm also going to show you my slides that I have, which might look a little bit better because they're fresher. Yeah, I guess. Well, not that fresh, but and then that way you can determine. I think it gives pretty good resolution. I've used a lot of different microscopes in grad school, including the Citation 5. I used it for the end of my grad school, and I did a lot of high throughput imaging. I also used anywhere from a low-end epifluorescence microscope that was from Nikon, that was from the 1980s. This looks way better.
Way better.
But it's not going to compare to an LSM 990. Your high-end scanning confocal.
No,
you know,
we're not looking to replace that.
You're looking at well, the LSM is like 1.5 million US compared to this. Is much more affordable, especially for not a core facility. It's just a lab. Shared equipment, that'd be fine. So our software is called Gen 5, and you guys are lucky to be my first group to get the newest version. It came out
A week ago?
a week ago, essentially. And there are quite a few improvements. There are quite a few imaging changes. You saw that splash screen earlier. It said Agilent. It's because we are now part of Agilent as of January. When you open up the software, you're going to be presented with something called a task manager, and this is where you're always going to be starting off. Does everyone know how to use like a plate reader in general already? Everyone's used one. Do you need a run through? I'll do a quick run through.
That'd be good, yeah. Like I've used other biotech plate readers, but not a citation. But I imagine it's gonna be very similar.
Did you use like the Neo 2 or the Synergy or the Epic?
I don't know.
Do you remember what it looked like? Was it a small
Gray and rectangular, and without any imaging or.
Was it very cube or was it more rectangular?
Was more higher.
Oh.
Probably H1.
Okay.
And the gray ones were the ones a little bit like longer time ago.
It was
because we
pretty
switched to the
old.
white cases.
Yeah.
But it sounds like definitely a synergy. And
Yeah.
it would be very similar.
That sounds.
Yeah,
that sounds
software is still
familiar.
the same.
Yes.
Software is still the same. Okay.
So when you hit read down, well, that's going to be defaulted at first. This is primarily where you're going to go for your plate reading. So if you have a standard curve and you want to read something, you're going to go straight there, and you're going to go hit new. This is going to bring up your procedure window right here. This is what it's called, and you could think of this as an area to. Yeah, if you want to just.
I can definitely move it that way.
Absolutely in the way.
You're on.
We also have 2 chairs here in case it's
Yeah, because I've seen that, so you guys.
No, I'm actually going to get out of the way, so if you want to move in a little bit closer.
Oh, you're filming it, I'm assuming.
Yeah.
Okay.
Yes.
So here's your procedure window, and what you could think of this is going to be your I guess modern day, like if you want to call it like a script writing area. You would put everything in here in sequential order, and then it would play in that order. And the most easiest thing to do is read. If you hit read here, this is where you're going to be presented with your plate reading stuff. So again, absorbance, fluorescence, luminescence, and it's as easy as just hitting OK. Well, I mean, choose what you want to read first, and then hitting OK. With absorbance, you just type in your number, and you could technically write up to 6 different ones, although I've never seen anyone do that much, but they can be there. You do have different options. So read speeds here, you have normal and sweep. You're probably going to all forget this, but if you don't, and you remember this, normal reads the center of the well 8 times and gives you an average, whereas sweep, it'll move very quickly. If you're doing something that requires a lot of speed, it'll only read 1 time in the center of the well and move on. I do want to spend a little bit of extra time talking about fluorescence intensity readings. So here you would type in your excitation and emission spectra. This is, if you're using like a kit from either like Promega or Invitrogen and you need to do a read, you type it in here. You do have options for reading on the top. So if you're reading a homogeneous solution, or from the bottom, if you have a optically clear plate and you want to read some cells that are expressing perhaps GFP, you can do that from the bottom as well. One of the cool things about this is if you ever forget about your spectra, you could always come here, and let me go back. There's this button on the left hand side right here. It looks like a little, I guess 2 peaks right here. You click on that, it'll bring you to here, and you can kind of choose whatever you want in here. So here we have, like, for example, Alexa 4488. Now you can see your excitation and your emission spectra. While this may not mean a lot now, it actually works out really well, especially if you want to look at, you could use this as a reference for multiplexing multiple colors and making sure that they don't overlap. For your plate reader, it does have a variable bandpass, meaning that you could actually move these and make it narrow and make it longer. So say for example, we're reading Alexa 4488 as a plate reader and you just really have a low signal, right? What you can do is, instead of only picking up the peak, you could actually open this up a little bit more and then get that tail end right there to pick up more signal. So this is one of the other ways for you to have kind of your customizability to either to make it very, very stringent and make it very tight, or to open it up to get more signal out of a really weak signal. You could add multiple colors here. This is one of the things I like about it. So if you want to look at Alexa 647, you'll see that they don't overlap, which is great, right? You don't get any overlap in terms of signal, and it's just a really good way to visualize your emission and your excitation and emission spectrum. But otherwise, everything else is the same. You would push in your numbers right here. You would put your band passes on the right hand side. You hit OK, hit play, and then you go. Now, actually, what I'm going to do is I'm just going to add something here just to show you. So here is, where I was talking about earlier, where we could write scripts here. In this case, what it's going to do is it's going to read your fluorescence at this wavelength. However, if you wanted to add, say for example, a heating step, if you wanted to run this at 37 degrees, you could technically click on set temperature right here, and then by default it wants 37 degrees. Here it says gradient, and what a gradient is this is very important for imaging. If you're doing live cell imaging and you have medium there, what will happen if you just incubate it at 37 degrees is you'll start getting condensation on the lid. So to prevent that, what the system will do is it has 2 elements on the bottom and 2 elements on the top. Your gradient here will be changing the temperature on the bottom and temperature on the top. So if I put a 2-degree gradient right here, the bottom is going to read 36 and then the top is going to read 38. So 2-degree difference. And if I click OK right here, now because my set temperature is below my read step, it's actually going to read first and then turn the temperature to 37 degrees. But if we didn't want that, then we want to grab this and then bring it up to the top. Now that's the correct way to write kind of your script. You do have a variety of other options. So you do have a shake dispense option right here, and then also what you were talking about earlier, which is well known, where you could dispense in each well and then read after each dispense. Any questions regarding just the plate reading part? It's pretty straightforward. All you need to remember is that read button right there, and then once you get that far, then you can kind of then if you forget everything, if you remember that button, it'll get you there. Okay. What I do want to focus on, and I think what is more interesting, is the imaging portion. My background is in imaging, and it's my specialty, so hopefully I can share some knowledge for you guys. Let's see here. Let's go back. Again, Task Manager. This is the first window. There's something called the Imager Manual mode, and I highly recommend everyone start off here when they first use this software and use this instrument, just because this Imager Manual mode is going to remind you of just a regular epi-fluorescence or wide field fluorescence microscope. You have your, your eyepiece, which is going to be digital now. You have your focus, and then you can change your objectives. So I'm going to click on Capture Now, and it's going to open up the Imager Manual mode right here. Now, this is going to be very important. With automated imaging and with imaging in general, you'll need to choose or define your vessel type. What I mean is, whatever you put inside the carrier, you need to define that. And we do have a variety of different plate types already written in here. So for example, if you have a Falcon, a Corning, a Griner plate, if you're using slides, you want to choose that in here.
Does it also do like micro chambers and stuff like that?
Let me know which one it is, and then I'll set it up for you. It's a little bit more, well, I mean, we have some in here already, like if we have some IBD slides, but if you're using like lab tech slides or mat tech slides that are the chamber ones, let me know. Give me the catalog number, and then I'll program one in for you. Yeah. What do you use right now?
We are not using any right now, so we can easily go with what is already programmed.
Okay,
Like
okay.
in case we need to do like, I guess like chemokine kind of, assay, migration assays, things
Sure.
like that.
Sure.
Yeah, just
Okay.
for down the road.
Yes, yes,
Yeah.
yes. Always email either me or Matthew, and then we'll take care of that for you. If you want, I could also show it to you too. Although that just takes a little bit of extra time, and it also requires a well, if you don't want to talk to the manufacturer, it requires a digital caliper. That way you can do all the measurements, because it's very strict in terms of the measurements in terms of microns. So if you're even if you're a few hundred microns off, it's a big difference. So here, what I'm going to do is I have an Agilent plate in here. So I'm going to click on micro plate right here, and I can, if I wanted to, even narrow it down further by clicking 9612 plate, because that's what it is. And here I'm greeted with a bunch of 9612 options, from generic 9612 plate to Corning, CoStar, Falcon. Those are all technically the same brand. And then you have your grinders right here, and the one that I have in there is a micro clear right here. No, I have an Agilent one. Sorry, I always say grinder because hint, Agilent
Is required.
is grinder. Yeah. So it actually works out the same way. But if I wanted to, I could just choose Agilent. You guys have Agilent or Griner as a company? Do they sell the plasticware here?
I don't know.
We order them from Sarsted, so I don't
Okay.
know.
Okay.
Yeah, but when we start doing the Promega assays, I think I used to use the grinder ones, like the wide wall plates that we haven't ordered yet, that I'll look into.
Well, if you ever decide that you want optically clear plates from either Griner or Agilent, just realize that they're both the same, so buy whatever's cheaper.
I mean, Agilent just gets expensive.
Okay, so I'm going to turn this off real quick. So let's talk about kind of the layout first. So here's your digital eyepiece right here. You have your scale bar right there, but what's most important is going to be the left-hand side right here. For your first drop-down menu, this is going to be where your objectives are. So you have your 4x, your 20x, and your 60x. Next is going to be all of your channels, DAPI, GFP, your PEQ, sci-fi. You have bright field. You have high contrast bright field, which is really good for if you're doing migration essays. And you have color bright field. Now, the camera here is a Sony CMOS camera that's black and white. So the way that we achieve color is we just put filters in front of it, red, green, and blue. So when you do the imaging, you get 3 channels. There's this find image button right there. I highly recommend you do not press that button. And it's because while it does a really good job at finding your image, meaning putting it into focus and also getting it into a good exposure, I don't like using it just because it takes a little bit longer. You can achieve the same thing by yourself if you just hit auto expose and autofocus twice. Find image does that 8 times. So you can imagine you being able to do it faster. Talking about that, you have your autofocus and your auto expose. And over here, your double up and down arrow versus your single up and down arrow, that's going to be your coarse focus and your fine focus. And then this number on the right hand side, that's going to be your bottom elevation. So what your bottom elevation is where the bottom of the plate is, it corresponds to the bottom of the objective. Your plus and your minus right here is going to increase and decrease the exposure. And this is all kind of like this is where you should begin in terms of if you're new with imaging. When you become a little bit more advanced, or you like to control things like I do, I am a control freak, you could actually open it down like there, and then you're given your exposure settings and your analog gain. So everything right here if you wanted to, and your LED intensity. Kind of all at your button right there. There we go. See, you see some stuff, some blue stuff. These are.
So with the like adjusting the focus and moving the lens around, like I guess there would be a limit as to how far it goes, because like on an actual microscope, oftentimes students can crank it too high, and then the objective is touching the slide and all that cracking stuff. Like that would not be a problem here, would it?
So by default, no, it's not going to be a problem.
Okay.
So these are air objective lenses, meaning that you're never going to be able to get too close
Okay.
to your sample. It won't allow you to, unless you turn off the safety features,
Okay.
which I do sometimes, and then it'll allow you to do it. But to be honest, the only way that you would actually be able to hit something with the objective is, say for example, I choose this, right? Or say for example, I tell that there's a 96-volt plate in there, but I put this in there.
Oh,
Because this is a different bottom height,
yeah.
it might crash into it. So if you choose the wrong one and you try to go all the way up with the safety features off, then you'll hit it. But you have to know how to turn it off, the safety features, and they're on by default. So unless you want me to turn it off.
No. We will not touch that.
Let's see here. I'm just going to turn it on so you guys can see something right there. You have a histogram right here, and well, I guess the next question is, what's everyone's level in terms of imaging? Do you guys already do imaging on a daily basis, or is this something new for you guys?
We're newbies.
Okay.
Masood has experience running a microscopy course, but he's
Usually by 2-photon microscope.
Oh, nice. Okay. Okay. I guess I'll give you some things that I learned in school that might help you in terms of taking better images. With the histogram, it's very nice because, well, when it's on, it'll give you kind of your dynamic range, basically going from left to right. Now, if you ever want to compare 2 different images in terms of intensities, you can never go past this dynamic range. Otherwise, you hit the limit of detection, meaning that the camera is not able to collect all the photons, essentially. So in this case, when I'm looking at here, I'm almost hitting to the most bright area, and you can tell. Let me just crank this up real quick. Oh, I'm gonna have to crank this up a lot. So here on the right hand side, you'll see that I'm basically over on the right side. That basically tells me that I am overexposing my image. Now, I'm only looking at nuclei, and I'm only interested in perhaps counting nuclei. In this case, I don't really care, because I'm only interested in counting them. If I'm interested in comparing intensities, then I would have to take that into consideration. One of the ways that you can tell where the overexposure is this little button on the left-hand side. If you click on here, it'll start shining a different color, and that's going to show you where the overexposure is. And this might be important, because if you have a really good sample that you made, but you have a little piece of lint in your sample, that lint is probably going to be brighter than your nuclei, essentially. And if that's the one that's overexposed, that's okay. To move, and actually let me go back. If I click on that well right there, A1, this is where I can move between the different well types of the different wells. And also, this right here, this little circle right here, that represents my well. And that square represents my field of view. So with a 4x objective in a 96 well, I could capture about 70 to 80% of my well, which is not bad. When I start moving to higher magnification objectives, that square is going to get smaller. If you wanted to move, you could grab and move to different areas of the well. You could also click on these arrows right here to move. And within the circle itself, you could also click to move around within the well. Just like that. Of course, this is going to be more important when you're at higher magnification objectives. We do have a variety of other tools right here that I don't necessarily want to go over today, because not a lot of people will be using them until they become a little bit more comfortable with the instrument. And it really takes about a month or two before you get comfortable with the instrument, and then you actually come down knocking on my door asking me, hey, how do you do this? And then I'll call in and I'll say, okay, let's look at it together and let's see what we can do. But because this is in a manual mode, you could just treat this as using it as a regular manual instrument, where you would take a picture, maybe save a picture for PowerPoint presentation, because you just want to show your PI that something worked. To take a picture, there's this little camera button that you might not be able to see. It's always down here, right here. Sorry, guys. But if you press on that button right there, what you'll see is that first image comes down here and creates, this is what I call a ribbon, and it'll just start stacking here. If I move, if I don't move, but I change my filter, and if I hit auto expose, what we'll see is this is GFP, and I just want to get that into focus real quick. Now remember that when I hit that autofocus button, it's going to go up and down the z-axis to try to get into focus.
So in terms of like when the laser is turned on and off, while we push the buttons, does it stay on then, or does it like make an image and then?
Right now it's staying on.
Okay.
The LED is on right now, and I'm going to be bleaching my sample as long as I keep it on. It does have a 30-second timer. I'm just going to snap that real quick. Or if you don't want that timer, then you can hit that off button right there and turn off the LED. So you can preserve your sample. I just took 2 images. I took an image in the blue channel for the DAPI, and then I took an image in the GFP channel for GFP. It's actually the GFP protein. And even though I moved up and down to get into focus, because I didn't move in the X or Z or X or Y plane, it actually overlays for me. They are 2 separate channels, so when you do export them, they're still 2 separate TIFFs, but they're automatically overlaid together, which is very convenient. What I do want to check now is to see if I could get anything in the red channel. I don't think so. That's probably autofluorescence. Actually,
hopefully they are okay.
We can play with it tomorrow.
Yeah.
Or Wednesday. Tomorrow is better. Tomorrow is when Aaron's gonna be here.
Sure, yeah. At least some color should work.
Okay.
Then we can play with titration.
Yeah. But now we have this, it's much easier to play around with.
Exactly.
I'm gonna switch over to higher magnetic objective. That way you can kind of see a little bit better than these little dots. I don't know if it's a good idea if you guys could turn off maybe these lights up in the front right here. Is that possible? So all I'm doing right now is I'm just going back and forth between auto expose and autofocus. To be honest, this is the easiest way to use it in the beginning. And then after you become a little bit more comfortable and you know exactly what you're looking for, then you could start moving into manually focusing and manually adjusting your exposure settings.
So you're just adjusting it based on the saturation, like your histogram on the top.
Typically, yeah.
Yeah.
Yeah. And there is one tool, I guess since we're talking about it right now. So if you notice, I just brought it down because I didn't want to oversaturate it, although counting, it doesn't really matter. But another thing that you could use is something called a line tool. This is going to be very important for doing analysis later on. A line tool is exactly what it sounds like. You draw a line and it gives you your kind of your intensities, your intensity values. This line represents this line right here, and what you can see is on the bottom, this going straight is considered your background. I would say anything below maybe 2,000 or 3,000 would probably be acceptable. Anything higher than that would, you'll see it, it'll look a little bit different. And then you have your two mountain peaks right here, which represents both the nuclei. This is going to be important later on when we talk about how to do certain analyses, and I'm going to explain to you what kind of analyses our system can do. But if I like this image, I could again hit the snapshot button right there, and then if I wanted to switch over to GFP, change my exposure. And I can tell you just by looking at this that this plate is probably getting really bad just because there's a lot of that green fluorescent background already. And I can tell just by drawing this line right here, and my background is already 10,000, almost 10,000, so it's definitely becoming a bad plate. But that's okay. This is going to be a good example for me to show you what we can do afterwards. So after, so I took two images so far, one at 4x, one at 20x. And at 20x, you can see that's apparently a little bit more, there's a little bit more background. If I hit this process and analyze button, what this is going to do is this is going to go ahead and bring me into my processing mode, and this is where kind of the magic happens. So, how many people have used ImageJ so far? ImageJ, almost everyone, right? So ImageJ is cool, very great, because it's one, open source, two, it gets updated very frequently, and three, I mean, almost everyone uses it. What's not so cool about it is that it's a little bit more difficult to use in terms of all of the things that you can do in terms of image analysis. One of the things is background subtraction or background FLEC. I'm going to give you a very good example by taking this line tool and drawing across, let's see, here we go. I'm drawing across two nuclei, which is represented by the two blue lines right there. My blue line going across is very low. That means that it's low background, and the way that I can tell If I just turn off my green channel and look at my blue, look at that background, super dark. That's perfect. However, when I turn that green channel back on, you can see there's a high level of background. Well, if I click on this image pre-processing step right here, if I click on that, and I'm just going to leave everything at default, I'm going to hit OK, hit yes right here, and you'll see that it actually subtracts the background really well. And it's actually a little bit overexposed, but that's because by default what our system likes to do after a background subtraction, it actually likes to make everything pop. You could just turn it off, and that's your signal right there. And if you see now, your background is very low. So this is an appropriate style of doing a background subtraction because it's done across the board evenly. So when people say manipulation, this is an appropriate way to manipulate your data. Talking about manipulating data, your raw data is always going to be there. So whenever you're doing your analysis, you're never going to be overwriting your raw data. I actually used one of our competitor companies' system when I was doing a postdoc fellowship. I submitted a manuscript and they asked me for the raw data. I sent it to them and they said that that's not the raw data. Yeah, it's a Japanese microscopy company. Well, I was doing my postdoc over there. And so what I had to do, I had to re-image all of it and then submit it. But then now it's accepted, so it's okay. So long story short, your raw data is there. That's a good thing.
So with this image, like the background subtraction is done on this set of images. If we now want to take, images of other samples, is there something you have to do to apply the setting to your next?
So if it's all in this ribbon right here in the manual mode, for now, I did the application for just the first one, I think, and then afterwards it asked me if I wanted to apply to the second one. So that's one way. The other way is when you start writing protocols and you start doing experiments to transfer the single image to your entire 96 well plate. It'll just do that for all of them. And what we want to start getting you guys comfortable with is going into this manual mode, taking a very nice picture, and then applying it to all of your wells. And then after that, say that's experiment number 1, right? Next week you do experiment number 2. You're going to open up that same protocol, which has all the same values, and then run it again. And it's okay to compare those because now everything is processed evenly. Yeah. So nothing changes. So that's how you're able to compare from not only from your day-to-day variation, but also the analysis. Yeah.
What if among the 96 well players, one of the well is not giving the good results? So can I change that only one well by manually?
You can manually, but then now you can't compare that one well to the other wells, right? Right. Yeah. Well, I guess it's what you want to ask, right? If you're only counting the number of cells, then it doesn't matter if you change intensity levels or change the brightness or whatnot, just because at the end of the day you're counting. But if you're looking at expression levels of a certain tag protein, or you're looking at expression levels of proteins that were chemically conjugated, then you might be using integrated density as a measurement, which takes into account the intensity plus the area. When that happens, then you do have to keep everything evenly, keep everything the same, otherwise it's not fair to compare. Any other questions? Okay, image deconvolution right here, this button right here, works well when you're at high res and when you're looking at certain applications such as cytoskeleton, mitochondria. Works very well. I actually call it the poor man's confocal because it gives you that type of resolution. So what does it do? ImageJ does also have a software-based deconvolution. However, ours is kind of like a mixture. It uses mathematical algorithms to determine where the scatter of light is that's coming from the wide field. Ours is, when I say part software based part hardware, we sourced our objectives from Olympus and we know where the scatter of light is. Not we. I'm not really good at math, but someone came up with all the angles and they were like, scatter of light here, scatter of light there, we should remove that. So they could actually subtract that scatter of light and then show the real light. And this works really well with the cytoskeleton and mitochondria to get you those nice dots. Yeah. It's a cool feature. Works really well with high mag. High mag being 20x and above. Let's see here. Next, I'm gonna go click on this analyze button right here. And is there something? Yeah, mice over there that are a little hungry.
No.
Do you want to check real quick?
It's a ghost.
With analyses, this is where you.
Oh.
What was it?
It's just a ceiling fan.
Oh, okay. Analyses, you have two different types of analysis steps. You have image statistics and then cellular analysis. So with image statistics, what that's going to give you is it's going to basically give you your global statistics, meaning what is the average mean of your blue channel? What's the average mean of your green channel in this entire picture? It's going to give you the total area, the maximum GFP channel and DAPI channel. Now, is this important for your application? It's going to really depend. If you're looking at, say for example, you're looking at lipid droplets in cirrhosis or something like that, then you could start using this type of strategies to start doing your analysis. In this case, it's not very fun for me. So I actually don't typically use the image statistics, but I do like using our cellular analysis. Our cellular analysis is going to give you object-based numbers, and by default, our system was built to count cells. At the end of the day, that's what it was used for. And then we started building in a bunch of other little cool features, subpopulation, using stuff like circularity to include or exclude stuff. So here, you're always going to see a start button right here, and here's your detection channel. So what we're looking at is we're detecting the DAPI channel, and I always just recommend people when they start here just to hit the start button and see what it gives you. There you go. So see, it does a really good job at counting cells.
So if we were to do like an alley spot, it could work like this, right? And it counts spots.
So about that, yeah, when I got that email regarding LA spots, I was trying to figure out, because I think 95, 97%, maybe 99% of the LA spots that I saw are upright, require upright imagers. So like our citation 7, scanners like the CTL, stuff like that require an upright imager, because usually with LA spots you have like a membrane, right? And then with that membrane you have to image from the top because it's opaque on the bottom. So unless you're using something that is clear, then we wouldn't be able to do LA spots here.
We could do a cycle spin followed by, we could spin the cells onto a clear bottom.
Yeah, sure. Then we could
And then
do the
detect
count.
this way. Yeah, this would be.
There-
It doesn't have to be a membrane, I guess.
I have heard of one company that has like this clear type of membrane that they use for this LA spot that's compatible with inverted imagers.
Oh, really?
However, I don't remember the name of the company, and I haven't seen it since.
Okay.
Most people are using like the Millipore Easies for the LA spots. So if it's membrane based, it has to be an upright imager, which this one doesn't support. But if you
Okay.
have anything where you could read from the bottom, yeah,
That
definitely.
would work.
Yeah, doing single color counts, dual color counts, definitely not a problem. So that's it's doing its cell count on the top right hand side. It counts a total of 8 cells. It does by default give you a variety of different parameters such as object size. You have your area, and then your means. And here, while it doesn't mean a lot right now, you want to start using. You want to start thinking about how you're going to do your analyses moving forward. So, for example, for flow cytometry, you would tag a variety of different proteins, and then you would see which one's positive, which one's negative. You look at granularity, all that stuff, and then you basically get one of those grids, and then you could select out a population. Here we would want to try to apply the same thought process except with imaging now. So, for example, if I had this right here, I counted this number of cells, and maybe I want to see how many percent GFP transfected are positive, right? So that's basically doing the selection process. What I could do is I could say within my object, which one has GFPs? So this is one way of starting to think about how to apply image analysis to answer a very simple question. It's just as like GFP transfection efficiency, or which kinds of cells have which protein, and then find a percent, right? Looking at ratios. Let's see here.
So here cells are picked out based on their GFP, right? Can we pick cells out of like a wide field, like a bright field image based on the contrast?
So right now it's counting based on the DAPI channel.
Okay.
And are you talking about maybe counting
Like
the
without
number?
fluorescence, but like the total cells that are there.
Sure. So you do have a high contrast bright field aperture in here,
Yeah.
which is a separate addition that goes into the phase annulus section, and that actually does a really good job at counting label-free cells up
Okay.
to about like 80%. Anything after 80%, it becomes a little bit inaccurate. But how that works is with the high contrast bright field aperture, whenever you move slightly out of focus, and this is a strategy that a lot of people use. If you take an image that's slightly out of focus, you'll see that the contrast is much greater, and you could use that contrast to determine how many cells there are, essentially. We do use a variety of different processing techniques, and if you have cells ready, maybe tomorrow we can do that.
I don't think we have cells. We just have slides.
Slides?
Yeah, and it's like tissue slides, because that's something else that we want to be able to pick out cells from a tissue. Like, for instance, plasma cells making specific class of antibodies within a complex like pancreas section, and that's counterstain for like beta cells, and so that is what we want to look at tomorrow. But then we will be looking
Okay.
at the cells. It's just in the context of its
Okay.
tissue environment.
Okay. In that case, how about who'd be interested in doing label-free cell counting? Is it just everybody, or I mean, I do have data sets on my laptop that we can go over and I can show you guys how it looks like, but without a real sample, it's a little bit difficult to show you how to go through it, just because the processing strategies are a little bit different, and in order for me to explain it in a manner that it's best to have like a live sample to show it to you.
Okay.
Yeah, so I'll bring my laptop in, and then maybe we'll talk about it tomorrow.
Yeah, I mean, we cannot just sack a mouse and get the cells out.
Oh no, yeah, no. Yeah, typically, I mean, it'd be nice to have like cancer cell, like something that would grow, not
like-
primary cells.
I mean, I have some helas I can
yeah,
see.
helas. Are they in a 96 well?
Yeah.
Yeah, hey.
That's
Okay,
good.
pretty cool.
Maybe if you could do like a serial dilution, that way you have like different concentrations going down. Would that be possible?
Yeah, I think so.
Okay. Cool. Yeah.
So it doesn't work well with primary cells?
I mean, it works well with almost. I think the cells that it doesn't work well on are probably cells that are very, very circular already.
Hmm.
I mean, it does work pretty well with them too, because then it adds less. It works well with a lot, I guess you could say. It's going to be dependent on cell type. What I've used it the most with though are fibroblasts, just because the companies like Impossible, you know, like the beef alternative companies, the plant-based companies, they all have to do cell proliferation studies, and they're all doing counting of cells label free. So then that's my main group of people that use that particular one, and they're always counting cells. Like every 6 hours, they'll count the number of cells to see what rate they're growing at, essentially. So primary cells.
I guess it's also not adherent, so
That's not a problem
That's
as
not
long as
an
you spin
issue?
them down real quick.
okay.
It could just be like a 20-second spin down. Yeah, 250 G's or RPMs or whatever. A low spin, spin them down real quick.
Okay.
Or just have them settle after like 20 minutes, and then we count them. Yeah.
So if we do like a trypan blue viability kind of state to the cells, would we still be able to count them? Because it would not have like any signal, that it would just be the color of blue in the dead cells.
So I have scripts that I've written for hemocytometers, which is the same thing. So
Okay.
it should be doable. Yeah. Is it you're,
Goodbye, cell counting. Megan is thinking to herself.
You can have like a full-on set where you can get like a hemocytometer with like an app that comes with it and like Triton Blue and everything. I think you still have that, right? Do you know?
Yeah.
Which is like specifically if you want to do cell count with Triton Blue. It's just like probably also like as Ann said, like he can help you like setting it up with like a normal slide, but we have like full-on like cell counters.
Yeah.
And yeah, so you wouldn't need
Yep.
to with this system. You wouldn't need to never use a clicker again.
So I worked with maybe 2 or 3 months ago. I worked with a CRO company that needed cell counting, and they wanted to use their own hemocytometers. You can imagine that with regular hemocytometers, there's lines, right? The grids, right?
Yeah.
And that definitely plays a role into how, you know, to the detection of the instrument of the cells. The way that I got around that is by using circularity. So because when you use trypsin, the cells round up, right? So they're typically all circle. So I would use that as an inclusion criteria, and it worked pretty well. The kit that Ann was talking about is actually a separate software package that is made to be much easier. You just one click and then it does everything for you. And it also it also comes with our adapter for the hemocytometer, which is different because if you try to put a hemocytometer in here,
Yeah.
this is a standard slide holder, right? So 75 millimeters by 300 millimeters. So probably might not be able to fit in here. You can try it, but it might get stuck. Or you get the other hemocytometer adapter. And then our hemocytometer doesn't have the grids. So that's the other difference. Okay. So going back to where were we at? Counting cells, and I talked about some of the numbers here. Oh, talking about image analysis. So what we're looking at here, there's something called a threshold right here, and by default it's set at 5,000. And in terms of, let me get my notepad and let me get a pen because I like to draw this out.
Do you want that chair?
Do you want it?
No, no.
What was I gonna say? Oh, so like with samples that have a nuclear stain and then some sort of other stain, are there ways to look at the overlap, like translocation to the nuclei, that kind of analysis?
Yeah, that's what I was talking about earlier. If we wanted to see like GFP % positive, right? So we know that right now it's circling the nuclei. So if we wanted to, if we had a protein like estrogen receptor, where if it's or one of the androgen receptors where it's found primarily in the cytoplasm. If you add a ligand to it and then it translocates the nuclei, could you calculate that? Yes, you can. Yes.
Okay, so yeah, we were picking out the nuclei, not the whole cell, based on that.
Yeah.
I see.
Yeah. Now, I did notice something. The software that you have right now is the plus version. There is a prime version, which is has dual masking features, and that might. I would say use this first. See if you like it. If you want to start doing dual masking, like say for example you want to see translocation from the nuclei to the cytoplasm, or from the cytoplasm nuclei to the plasma membrane, you'd need 2 masks, right? And then that would be our prime version. The good thing is if you ever do decide to purchase that, it's actually cheaper to upgrade than to actually purchase the entire system. So you actually looked out on that. If you want to upgrade, it's cheaper, I think.
That might be on Xavier's CFI, I think.
Yeah.
He
And
has a few things to add to this.
And if you guys wanted to test it too, I could just install a demo and then it'll just expire in 30 days. I personally like using it. Well, I have to use it because people send me their data and they're like, can you do this? And I'm like, okay, let me try. And then it requires multiple maskings. So I want to talk about kind of our algorithm on how we use what we use to do the analysis and how we identify objects. The algorithm that we use, the first algorithm, is called watershed method, and this is fair enough. Okay, so if we're only looking at the GFP channel, the green channel, here we'll see again this line being drawn from left to right is here from left to right. Our bottom section right here, that's our background. It's very low because this is a background subtracted image. You'll see that this peak and this peak is dramatically different. The peaks represents the intensities, right? This is much. Let me digital zoom in. You'll see that this is definitely more intense than this, right? So I'm just going to draw that here. Okay. Now, if these two were right next to each other, right, they would essentially look something similar to this, where you have 2 mountain peaks close together. Watershed is exactly what it sounds like. You could think of these peaks as mountain peaks, and this threshold value right here is whatever line that we use as a cutoff. And you could essentially think of it as your water line, something similar to that. So if you look at this image right here, at low tide, you'll see that these 2 mountain peaks represent one island. Okay. At high tide, when the water raises, all of a sudden you lose that trough of the mountain, and then you get 2 separate mountain peaks represented as 2 different islands now. So this is something that we use to separate or to segment cells, essentially, or segment whatever objects we're looking at. Now, this is kind of like the basics, the first step, right? You can separate it by using that thresholding right here. But what happens if you have a heterogeneous population, right? You're going to have some cells that are higher intensity, that have higher intensities than others, right? You're going to have a variety of different peaks. And if you start, if you have a bunch of mountains right here, right? And if you start increasing the water line above a certain threshold, you're going to lose your mountain peaks. They're now going to be underwater. And if they're underwater, well, you can't count them anymore, right? So that's essentially it. So we now have to be mindful about how are we going to be able to get all of our mountain peaks below this water line, but also be able to count two cells or two objects that are very close to each other. How do we separate that as two objects, right? Because that's what's the most important part is. And what we use, our second method of being able to separate them in this advanced detections option is called a rolling ball. Now, how many people have used ImageJ to look at their Western blot data?
Let's use similar ones.
So other ones where you have to actually draw kind of like your background to do the subtraction, something similar to that. Okay, with rolling ball, let me just draw two mountain peaks again. So a rolling ball diameter essentially is a square because pixels are square, not circles. I don't know why it's called a rolling ball, maybe because we're rolling through it, but essentially this is going to be your size. So if I say this is 30 microns here, in this case it's saying 300 microns, that means that this size is going to be 30 or 300. And essentially what this is going to do is actually going to roll through this section right here, and as long as it cannot fit into that mountain peak, it's going to be counted. It's going to roll through like that. So essentially you're doing a background subtraction that is like that. And the reason why this is important is because now it's taking into account variability in your image. So you have different intensities. You want to do rolling ball. So the first step is to do the watershed threshold, get as many cells as you can that are basically true positives, and then afterwards come in and then be able to segregate or separate these objects by using this rolling ball. This sounds like a lot today, but I like to explain this because it's going to be very important when you want to start moving forward, especially with the segmentation. A lot of people get hung up with this, and it's because they forget about the terminology. But once you get the basic understanding down, it becomes a lot easier to start doing your own analysis and start taking ownership of your experiments. There are a variety of other things that are in here, such as image smoothing. We're not going to get there quite yet until we actually have samples, because that's going to be an extra layer of complexity. Sometimes you want to use it because sometimes, say for example, you're at high magnification and you want to count nuclei, only nuclei. But of course our nuclei has nucleoli, or they have certain areas that are a little bit darker, certain areas that are a little bit lighter. If you do a blur, essentially a Gaussian blur, then you'll be able to take perhaps something that might be counted as 2 with our software and make it count as 1. That's generally the purpose that I use it for, although there are a couple other reasons why I use it. One being plaque counting or LS spots. I actually use it for that just because of the method of analysis. And we'll get there when you have samples, and then maybe we'll get on a call. Are you guys going to be installing internet on here? Going to be connecting it? Because it'd be very helpful if like me or Matthew could log in and then help you through, like say for example someone has questions and they don't exactly know how to do the analysis. We could either, people could always send us the data, or we could just log on and then check it real quick, because rather than having you spend like 5 hours scratching your head figuring out what to do, we might be able to answer in like 2 minutes. Yeah. So,
is that computer like Wi-Fi?
Yeah, it has
Yes.
Wi-Fi.
Oh, okay, yeah,
So
so
just
yeah.
have to connect. Yeah.
So,
I think we'll be doing that.
okay, so let's see. So in this case, I'm going to kind of do another subpopulation analysis where I am thinking about my GFP channel, and I only want to count out of the number of cells that I have here, which are 8 cells, I only want to look at cells that have a lot of GFP, meaning cells that are super intense. And maybe because I'm doing an isotype and I want to select, certain cells to pass through them and move them forward, and I only want the ones that are highly expressing. So what I can do is I could say only cells that have perhaps maybe this type of brightness or higher, and again, all I did was I clicked that little button right there, which has an arrow, and I just dragged it to one of the outlines, and then it automatically input that number. Or I could input that number myself, or I could measure all of these and look to see which one I want to include or exclude. There's a variety of different ways to do this. I'm gonna click there, and I could call this perhaps, my GFP positive cell count. And what will happen is, here are my 8 cells right now. That's what I counted using just the nuclei. Now that I added a secondary requirement, which is having a positive GFP of over, was it 32,000? It's actually only that one now. So everything else doesn't meet the requirements. Right? Remember that I used an alligator sign. I didn't say greater than and equal to. I just said greater than. So that's why it excluded that. So here are some kind of flow cytometry type analyses that you can do. Not necessarily full-fledged, but with imaging, especially with live cell imaging, you can collect data points. So instead of endpoint kinetics, or instead of doing, I guess endpoint kinetics types flow cytometry, where you have to have, like, if you want to do 3 time points, you'd have to have 3 different samples and then stop them at certain times. You can actually just monitor one well and then do 3 different time points with the same cells under the same conditions over an extended period of time. I'm going to hit on add step right here, and mind you, what we've been doing this entire time is everything in this manual mode, this easy mode that everyone should be soon get acquainted with, because it's just like your regular TC microscope. There's nothing hard about it. You can't break it. We did a capture, a process, and analyze. That's our motto. And what we now want to do with this one image that I took, I now want to apply this to all the 96 wells. There is this button on the top left-hand side right here, and it's called Create Experiment from an Image Set. And I want to repeat this again. Create an experiment from an image set. I'm going to say this again. Create an image from an image set, because I'll say this a bunch of times, and then next month I'll get the same question. How do I do that again? It's right there, that button right there. You click on this, and it'll bring you back to that procedure mode that you saw earlier, where we were doing plate reading, right? So instead of doing plate reading, now we're doing imaging, and everything that I did gets translated over. It remembered that I used 20x objective lens, that I used DAPI and GFP. It also remembered my exposure settings, including my actual exposure and analog gain. It even remembered where I took the image. If I just left everything as is, then it would just image the entire well. If I wanted to select a set of wells, on the top right hand side where it says full plate, I could choose my wells right here. Clear all. Maybe I just want to image these. I could do that. But maybe this one well isn't enough, or this one field of view isn't enough, right? Because I don't know, sometimes, at least with me, I did, I imaged 3 different random areas, and then I took the average of that, right? It makes sense. You can do that by a variety of different ways. I could choose defined beacons, and I could actually manually click on that button right there, that microscope button, go in, and then choose my 3 different areas. Of course, if I do that, I've learned that I'm a little bit biased, and that I choose areas that kind of look to what the experimental control is supposed to look like, and then I skew my results. So towards the end, what I ended up doing in my academic career was use something called montage. Now montage is basically taking tiles and stitching them together. Of course, that's not really representative, right? You want to get something that's kind of random. So by default, it sets so that there's a 10% overlap, and this 10% overlap allows for stitching to make one big image. What I can do is I could actually add in negative numbers here, and I could actually move them far apart. And this is now I have a 2x2. Now I get more, basically, n equals, right? N equals whatever. I have more numbers of cells. I could add even more, right? I could do a 4x4. Now I'm a little bit out too much. This might be a little bit excessive, but I could technically do that. You want to find the power of your n. That way you could figure out how many images that you need to take based on the number of cells you need. And this is going to be random, right? You're going to have areas that are going to be empty, but you're also going to have areas that do have cells. I'm going to go back to a 2x2 because that's going to be fine for me. That's exactly actually what I did before. And by doing this, I get the image again. These areas, 2x2 automatically. And not only that, not only that, what I'm going to do is I'm going to hit play right here, and I'll just let it run. And what this essentially does, is now it's going to go through our entire section of what I did from the beginning in our manual mode. Take the images, look at our blue, look at our green, count the number of cells, and then look for my subpopulation. And essentially this is supposed to help with streamlining your processes and also helping you reduce the number of bias, because that was something big that played in my research. So let's see how well this did. So again, not so bad, right? So we have our nuclei right here. Exposure settings, you could look on the right hand side, you can see that I'm a little bit overexposed. So that's just me choosing the wrong exposure settings. What I can do in the future is I could use auto expose. Auto expose works well for the first set of experiments, and then afterwards it's going to kick you out the exposure settings, and then you just apply that to your next set of experiments. Looking at the green channel, very bright. Also, you can see that a lot of background right there. Right? Now, hopefully, since you guys do have a really nice computer, you should probably be able to see the second channel. Yep. So my background subtraction already was applied here. And you can see that green haze that was coming from the green channel is gone now. And again, this is a well-accepted background subtraction or background flattening method that's done evenly across the board, so it's okay to compare amongst different ones. And here, so for our matrix right here, what we're looking at, our drop-down menu is going to include everything that we're interested in. The first one's going to be the raw image. That's never going to change. You're never going to lose your raw image. The second one is going to be that background subtracted image to remove the haze. Third, you're going to get your cell counts. You do get, by default, all of these other object information. Of course, we could always turn that off. If you turn it off, it just calculates faster. And also, you do get your GFP positive cell count, which is what I put in as a selection, subpopulation. Let's see, not quite yet. We'll just wait a little bit longer.
So once all the data are collected, can we go retrospectively and collect even more parameters from what has been reported? just like what we did in the first one, like when we did back to the one well, we can do the same to the whole plate.
Absolutely, yep. And great question. So, have you guys ever heard of cell painting? It's a technique that cell painting is some people are using as a general method where you do a multiplexing style of looking at different proteins. One being like the endoplasmic reticulum, one being like mitochondria, and two other things I forgot. But essentially, what they're looking at is small changes in differences. You know, you treat with a drug or you treat with something, and then there's changes in morphology. They're basically doing, and what I call it now is basically it's kind of like, you know, next generation imaging, if you want to call it NGS. Well, NGI, I guess you would want to say. But you know, if you took this image today, and then 3 months down the line, you're like, hey, I had those images, but now I have a different question. Sure, you could come back and you could reanalyze this image set completely differently, and it can give you a drastic amount of different what's that word? You get different data, essentially, based on what you're looking at. Here, this is very simple. We only have two colors here, and it's because the third color didn't work that well, just because of the filter sets that we have here. But essentially, yes, you can. See, so here we're looking at, you know, numbers. Now, we see trends, right? This plate right here it's actually a serial dilution. It's supposed to be from the highest to the lowest. We see one that's way out of bounds, right? So this is the review process. I'm going to come in here and I'm going to go, why is the nuclei so high in here? No, that's right. Yeah, it did. It did it right. So this is probably just because my plate is too old. So it used to be, yeah, that's right. Yeah, it used to be high to low. I'm assuming they all fell off. But you get your cell count, and this is going to be your total cell count right here. So essentially, if we come here, this is only 9. I'm expecting to see not that many cells. Yeah, and it looks pixelated right here. It's because these are thumbnails. What you want to do is on the left-hand side right here, you click on that, and you hit go, and it'll load the actual image for you. The reason why we implemented this feature is because there were a few groups that were using really old computers, and they were having issues being able to image at the same time as well as looking at the images. So if we look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the right count. Now let's look at my, quote unquote flow cytometry method. This is GFP positive cell counts, and it went from 9 to 8 right here, right? We can compare to our regular cell counts right here, from 69 to 61. So we want to start thinking about how to do your analyses and how to apply these various approaches to your experiments for image-based screening methods, essentially. So think about that in the back of your head. If you need to come up with ideas, you can always bounce it off with me. I take some time to respond, but I end up responding to people, so you don't have to worry about that. I do like bouncing ideas off other people as well. That's just part of the hobby that we get to have. That's kind of the gist of how you would go from starting from a basic imaging experiment in the manual mode and then moving over to running it kind of in an entire plate. Now there are a lot of other things that we should be discussing, specifically your applications, because that's going to be very important. We haven't even touched the surface of this yet. There's slide scanning, we have injectors, right? We're looking at, I don't know, you guys are doing like luciferase assays. Is that what you're primarily using that for, or?
More What's your assay?
Isocypherase.
Isocypherase?
Yeah.
Yeah, I think the Promega, we have several different kinds of detection. I think it's also chemiluminescence based, most of them. But we don't have those set up because those are experiments that we want to do when we know how to use it. So we have the more basic protocols like ELISA, and I don't know which exam we have.
I'm looking at Ross generation with mitosocs on some cells.
Mm-hmm. Okay.
Yeah, so those are the assays that we have planned. And Erin has a fluorescence assay, so she's wanting to measure the abundance of fluorescent tagged dextrin, so FITC dextrin in her serum samples, and that's coming up tomorrow afternoon.
Okay, cool.
Yeah.
Alright, that's gonna be fun.
And then some slides, I don't know if you mentioned that.
And slides, yeah.
Slides, yes. H&E slides.
No.
IC?
These are immunofluorescence.
ICC.
Can you also take a picture of twin here?
Yeah.
Yeah.
Oh,
Yeah.
So I do have some slide for it.
Okay, so we can also look at them.
Yeah, and then we'll go over how to do slide scanning, right? That's kind of a cool feature. Talking about, I haven't talked about file types.
Oh yeah, like how you export it.
Yeah, yeah, and also proprietary file types, how to save images, stuff like that. So, first of all, if you just wanted to save one image, and I'm actually going to use one of these images right here. That's gonna okay, these are really sparse. I need to get a new plate. That's what I need. Here we go. Okay, so something like this. There we go. Okay. So if I just wanted this one image, because I need to put on a PowerPoint presentation for a lab meeting in the afternoon, I can right click here, and I can just save right there. And you're going to be given two options. The first option is save it as raw data. Our raw data is always going to be saved as 16-bit TIFFs, black and white. This is something that you would use for image J to do your analysis on if you didn't want to use our software. Or if you wanted to use plugins that you guys already have. If you guys want to use image J, I have a perfect script for it that'll export these out and also put them into stacks, hyperstacks, if you want to do it that way. What more people are going to want is you save the picture for a presentation and leave it at what you see is what you get, because then you're going to be getting your scale bar, and then everything meaning your blue and your green channels overlaid as one in its actual color rather than just black and white. That's only if you want one image. If you had a large set of images, right? We took 4 images per well. If you did 96 images on 96 wells and you wanted to export all of those images, you could click on your plate, go down to batch image save right here, and then you're gonna be able to choose what you want to export. The top being your raw data, the bottom being the background corrected or background subtracted data. Or you could also always create your own data as well. So an example would be if you're doing some quality control and you want to make sure that you're actually identifying the correct number of nuclei, you know, that masking, you'd be able to export images with the masking if you wanted to. And then you could also export it to different file types. You're not only restricted to TIFF files, you can also export them as PNGs, GIFs, JPEGs. Of course, those are all loss files, not lossless. So you do get more pixelation at the cost of, well, at the benefit of smaller file sizes. Next, what I want to talk about is protocols and experiments. We didn't go over that. What I just ran right now with all of this data, this is now considered an experiment. But what I was setting up earlier was a protocol. So to talk about that even a little bit further, a protocol, you could think of it as a methods section for the instrument. For example, heating up to 37 degrees, shaking for a little bit, injecting something, taking an image at 20x, you know, doing the analyses, doing the subpopulation, whatever you want. It's not the actual data, but it's just the instructions on how to get the data. That's what a protocol is. An experiment is your protocol that you've just written, plus any data that you acquire. Why is it important? It's important because you can always pull a protocol. Say, for example, you start standardizing an assay in your lab, and you have new students coming in all the time, right? But you don't want them to, you don't want to have different data all the time. You want them to use a standardized protocol. That way, you can compare, you know, student A from 2018 from student B for now, right? Because you're using the same protocol, you're always going to get the same data. That's why you want to use protocol. If you start modifying that protocol and it's going to go into a new data set, it's going to always follow that new data set. And that's great because you're always going to have a trail. But you essentially never want to modify your main protocol unless you're planning on making that the main default protocol for everybody. Of course, everyone can also have their own protocols, right? Because I mean, everyone has their own projects. In that case, then you could decide for yourself whether or not you want to have your own folder with your own protocol, and then whether or not you want to deviate from your own protocol. So kind of like that. Your protocol is going to be a .prt, and then the experiment is going to be a .xpt. All the images are saved in the default directory in the public folder is documents.
So you said there was that button for new experiment, blah blah blah, right? And is there one for new protocol, blah blah, blah as well? Because the one that you repeated 3 times where you used to start a new experiment. Is there one to start a protocol, or is protocol generated with the experiment?
You can definitely start a protocol from scratch.
Okay.
I did not talk about this because a lot of people have a difficult time visualizing how to start that protocol. I can give you an example. Everything that we did right now in manual mode, where we took an image in the blue channel and the green channel at 20x, and then we did a 2x2, and then the analyses. I could open up a new protocol, and I could open up a procedure window, and then I could write all of that in if I knew how to use the system, right? As you start using the system, you could write it out yourself, or you could just pull from another protocol, and then take that protocol, modify it a little bit, save it as a new protocol. Maybe, you know, it was, you know, ON's good, you know, experiment number 1, and then all of a sudden I found a new way to do it because I got some new data from an article. I might call it, you know, ON's protocol number 2 now, or maybe because I'm now modifying this, going from a 96 weld plate to a 24 weld plate, that's going to be a modification of the protocol. But as long as I know what I'm doing, see, I could go to inverted imager, click on this, and then I could essentially write everything that I did. I had a blue channel, I had a green channel, you know, I wanted, well, this is actually exposures. I could choose my exposure settings, right? I could choose everything here. So the manual mode did all of this for me. If I wanted to go straight to the protocol because I knew how to use this, actually this is what I do now, then you have all you have the ability to do so, essentially. And I always think of this as a double-edged sword. Our software allows you to basically be open-ended. You could use the software, do all the modifications you want. All the options are open, even the advanced options, which are here. And while it's cool that you get all those options, sometimes people get overwhelmed, especially if they're a new person. So that's why I try to show the easiest way to use the instrument first. Once you get your feet wet, once you start working on it, once you run into issues, you're going to give me a call and you're going to say, "On, what happened?" And I said, "Let me see your protocol, and then let's work on it together." And then I'll say, "Oh, look, you just forgot this button right here. Well, let's talk about this new button." And all of this information that I went over today, and then plus some, is actually all in this image training manual. This is what this is. And what I would recommend, if you have a new student come in, new postdoc, anybody come in, you could actually open this up, and they have a bunch of buttons in here, or sorry, they have a bunch of images in here. Let me just go to that right section.
It's very detailed.
Here you go. Quick imaging guide. It'll first ask you the main question, yes or no, did you do something? And then after that, it then goes in and explains to you a quick guide to imaging and how to set up everything, where to go, and everything that I just explained to you in terms of going into the manual mode, which buttons to press. It has all the color codedness here. This is cool. All the way to advanced imaging information, such as how would you want to start doing Z-stacks, because you can do Z-stocks. How can you start imaging and then doing certain analyses? How to do label-free cell counting. All of that's kind of in here. And then it tells you certain parameters. It actually gives you a lot of information on how to be a better microscopist.
Does that come in an electronic format?
Your electronic format is located in this biotech folder right here.
Awesome.
And it is called Cell Imaging Training Guide.
Okay.
Right there.
We'll put that on our shared drive. It's easier to.
And if you ever forget something that I repeated 3 times today, it's right there. Because I don't know how many times I have to explain this, but it actually goes through the entire thing. But it actually tells you how to create it from going from manual mode to an experimental mode. So that's all here. What's included is also the documentation for the Gen 5 software, for the system itself, for Gen and videos. These used to be on YouTube, but now that we're part of Agilent, we took it off. But they're right there. Yeah. So, that's kind of it for now. Yeah.
I think, can you just show how to create a protocol from an experiment? I think this is what Sue was asking, because you create an experiment from an image file, right?
Oh.
Well, I think I'm okay. It's more for the lab, because it's very similar to the plate reading function as well. You either have experiment or you have protocol, and the protocol is something that is like a template that you would save and then use it later, and you can tweak it afterwards. So I think we're okay. I mean, we definitely need to go play with it, each of us, to actually figure out like how comfortable we are with it.
Just to complete that thought, because that is a good point. Say for example, you look at your colleagues, your lab mates' images, and you're saying, hey, they did a really good job. Can I copy that? Go to File, and then you can save the protocol as something else. That's right there. And then that way you can take it and modify it, of course, to your parameters that you're looking at, what you're interested in, and then it'll do everything else. So that's how you would do that. Yes.
We should have a list of optimized protocols that everybody uses consistently. But yeah, if there are specific things that need to be adapted to each experiment, then we can do that too. So.
Any general questions so far? What time is it right now?
So that software, that's like a permanent thing that we get, right?
Yes.
It's not gonna be like Flojo that updates to different versions and then we have to pay for it.
So no, you're not forced to upgrade to different versions. So anything that is, so right now this is a 3.12. If the next version is a 3.14, you're upgraded for free. If it's a 3.15, you're upgraded for free. If it's a 4.0, 5.0, if it moves to a big number, a big different number, then you do have to pay for that new software essentially. But it's not subscription based, at least not now. 5 years down the line, I don't know.
Who knows? Excellent.
You know, everyone's moving towards cloud-based solutions.
Yeah.
So who knows?
I do have a question.
Yeah.
You set up for experiment for one well, like A1 in a 96 well. So suppose I'm not happy with that well. and I wanted to go by another well to set up my everything for my 96 well. So how do I go to that? Like which option?
So if you wanted to use a different well to do your analysis,
Or how can I see the whole picture of my plate in a single picture? Can I see it?
oh well, I mean,
Like I remember when I analyze in CTL in a response plate, I can see the whole picture of my plate in a single picture. Can I do that in here too?
no, not quite. The CTL could, because it's a scanner, so it just scans everything. This is, they're all individual images. So you'd have to essentially look at this block right here, this grid, and then be able to go in and then start looking at them this way. So you could do it this way, where you go in like this, but to look at all of them in just one flat out high resolution, that's not possible with just the way that our imaging system works, and it doesn't translate well when you start doing more images. So if you're doing like a 3x3 or 4x4, those images start getting really small, and to be able to just try to show it all in one kind of full slide deck doesn't work, versus the CTL actually
Yeah.
just scanning. into
I
it.
remember sometimes like I choose A1 for 96 well, but that well is not good enough to resolution. So I go for like the another well. In that whole picture, I can choose for which well I should go. Then I choose that well and set up my experiment. Then I go for all of those. But this cannot happen here.
No, you'll have to unfortunately go into each well and look. Yeah.
But
and
like
that's-
later in the protocol, like there is a well selection. If you just had like a quick look which wells you want to image, and then you find the conditions in the protocol, you can technically then select those wells that you want to image, and you don't have to image all of them. You don't have to image the whole plate. So like as long as you look at them first manually and determine, okay, I want to do A1, maybe B4 and C11, then you can go in the protocol later and just click on those wells. And it's called in the well selection, and then image those ones in the automated way.
Yeah. If you really want to make sure that it's unbiased imaging, you could set up the parameters where you could
Yeah,
say.
it's because like I need to set up a threshold, so that threshold has to be in some specific well. So if that well is not like good enough for resolution, then that whole plate is not going to give me a good result. Just thinking.
I see. Okay, so your concern is well, okay, so ideally what you'd want to do is you'd want to go in, and this is going to be your first pass. Your first pass, you're actually going to find a good well, which is hopefully your positive control. Then you would image that, and then afterwards you would apply that positive control among everything else, right?
Yeah.
If your positive control, which is going to be, say for example, perfect imaging, perfect exposures, perfect analysis, if it doesn't work well with the other ones, then that's good, because then your wells that are sparse or your wells that don't have anything are a true representation, as well as long as you also compare it with your negative control. Yeah. I think maybe Anna, what you're alluding to is it the one where you could set certain parameters, like if there's a well that has an intensity of, say a blue intensity
Make a
of,
cutoff of those, like cutoff value for all of those oil, maybe the good one.
what was it?
Like I can maybe set up a cutoff value for all of those. Like
Yeah, exactly. And then you could also have the system scan each well before imaging.
Okay.
And I think that's what you're talking about. Yeah.
Yeah, in a spot I usually take a scan at first, all of those oil, then we take the picture. So we can do it here for it, scan all of those.
So what you could do is what you can do is you could use the plate reader to do kind of your selection process first. So if you're worried, say for example, you're worried that maybe certain wells don't have enough transfection, or doesn't have enough cells, right? If you have a threshold that you're looking at, say, your DAPI intensity is going to be a certain amount. If you have 50,000 cells versus 100,000 cells versus less than that, you could then scan the entire plate using the blue channel, right? Using 365, and then see which one has, see which one meets your threshold, and then only image those particular ones. Is that what you're?
Yeah. Understood.
Okay, then yes, we could do something like that.
More questions?
I'm okay to take individual questions if you guys are shy. You guys want to talk afterwards. I know some people don't like to speak up when there's a crowd.
I think the questions will come tomorrow when we're actually
Yeah.
doing classes.
Okay, yeah. Tomorrow's gonna be hands on deck. Get wet, get your feet wet, press the buttons, play around with it. I'm gonna be guiding you through how to use the system. Yeah. And since you do have slides, right?
Yeah, I do have slide for H&E staining and cytostate fast cleaning staining.
For your slides, do you put more than one sample on?
Yeah, more than one tissue. Yes.
Okay. What we can do, and I could show it to you, although I don't know how useful it will be with this particular setup. But we could just, if you do this a lot, and you don't want to manually go in and click your region of interest, we could actually go on at low mag,
Okay.
scan the entire slide, and then afterwards present you the entire slide, and then you just choose the region of interest. That way you don't have to try to go in there and click, where is it? Click. Yeah.
So what would be a good time to start tomorrow? For
What time
you
does everyone
guys?
usually get it? So I'm from California, and we usually start no earlier than 10. But I know that
10 is fine. I actually have a
I do have
meeting
class.
from 9 to 10. When is your class?
It will finish 11.
11, yeah, so 10-11ish.
how about,
I guess we
I
can
mean, I'm
start
okay
first.
with starting earlier if anyone wants to get a head start.
Well, I won't be here, but it depends on you guys, because that's the slides.
You won't be here also, or?
I'm coming in, but I have a meeting from 9 to 10.
Okay.
Yeah.
Because I have to be downstairs till probably 10 or 10:30 anyway.
Yeah, so let's start at 10:30, 11. Something like that.
Sure.
And one last question. So we cannot take picture from Millipore Maha plate in this software, like in this.
Which one?
Millipore Maha or for any spot. You talked.
Oh, no. Yeah.
No, not with the membrane.
Yeah.
Unless we find that membrane that.
Yeah. I remember like we used Millipore Maha plate for CTL counter in that previously. It's different plate.
Yeah, this one, we didn't think about alley spot at first, and we thought there's an alley spot in Lori West's lab. But I think it's still adaptable. We just have to optimize if we could just do a cyto spin, like spin cells down onto the plate and then count the antibody or cytokine positives. We could potentially do that. Yeah. This is very exciting. You guys know that we are one of the first ones to get this in Canada, right? So take good care of it. And
Where's the first one? Is there one other one?
I think this is the first
I think this is the first one.
Yes.
so
You're
Yeah.
like all the way up there with like the most innovative technology in the market right now.
So we expect
Incredible.
good data from it. And yeah, and then you guys should think about a name for it so that you take care of it.
And then for whoever's power users want to stick around, I'm gonna go over how to change filters, imaging filter cubes, and objective. I don't know if you want everyone to be okay with touching that, or if you
No.
only want select
I think the
users.
fewer hands that touch it, the better, actually. So Masood, you're okay to
Sure, yeah.
look at that?
Oh.
Alright. Thank you
Thank you,
guys.
guys.
Thank you.
Yep.